In this video, we're going to focus on quadratic inequalities, and they might be tricky at first. You got to figure out what inequality in a quadratic expression actually means. So, for example, if we see something like greater than symbol. So here's a quadratic, x squared minus 2x minus 3. Not sure why I put an extra x there. And so if this quadratic is greater than 0, what does that mean? Well, first thing you want to do with quadratic inequalities is solve for x. You're going to find the x-intercepts. Where does the graph cross that x-axis? And then you're only going to focus on the domain values, the possible x values, when your y values are greater than 0. Remember that if this is our function, essentially this is saying that where f of x, where the function is greater than 0, which is essentially saying where your output is greater than 0, which remember are our y values. So where y values, good lord, that's messy. Where are our y values greater than 0? So we want to solve for x where the y values are greater than 0. In other words, we're going to state the domain, possible x values where y is greater than 0. This is what it all boils down to. All this fanciness right here is really saying, give me the possible x values or the domain where y is greater than 0. So let's break that down actually with our graph here, see what it looks like. Alright, we're gonna practice a couple different things here. First thing, let's start with that quadratic that we had here. Where it's greater than 0. So our first step was to solve for x. So if you see a quadratic in general form and you need to solve for x, a few different ways you could go. I always like to check 3 different things. I like to check for factoring first. Can I factor this? Because that's always the easiest, most fastest way to do it. And I think we can. So if we use 2 sets of parentheses, x in each of them, factors of -3 that add up to -2, well, we know that -3 and +1 will multiply to get -3 and add up to -2. So we just factored it quite easily. We know that our x values are where this equals 0. So how do we make this whole thing cancel or equal 0? If we make x equal to 3, or if we make it equal to -1. So there's our x-intercepts at 3 and -1 here. And now most times we would use closed circles because these are included in our graph. But for inequalities, especially for this specific inequality where it does not include 0, we do not want values that include 0, so I cannot put closed circles here. I need to put open circles. And our parabola is going to open up because a, that value right there, is a +1, so we know we're going to have a parabola opening up. We know that our vertex is going to be somewhere down here using our line of symmetry. Somewhere down here, but it turns out that it doesn't matter what any of these values are, what any part of this graph is down here, because we're only interested in the values where y is greater than 0. So we're only interested in this portion of the graph. We're only interested from here up and from here up. We're only interested in the domain from this value to the left, and we're only interested in the domain value from right here to the right. We do not care about any of these values where y was less than or equal to 0. All we're caring about is where values are greater than 0. So let's describe the domain, the possible x values, where y is greater than 0. Alright, we're going to use interval notation. If you don't know what interval notation is, I suggest you watch that video first. So we know that possible domain values are going to be from -4 out to infinity, and we always start with our most least value. So we're going to start with -infinity. We can't include it, so it's an open or parenthesis. And we want all those values all the way up to, but not including -4. So again, it's open at -4. Okay, but we also have more domains where y is greater than 0. We jump over to this side. We're not worried about anything in between. And we're going to start with 3. But we're not going to include 3 because that would equal 0. We want it to be greater than 0. So we open or parenthesis at 3. And then all the way out to infinity. Positive infinity. So another parenthesis. So here is where interval notation starts to get interesting, because we have two sets now. We don't just have one set. We have two sets of domain values where y is greater than 0. We're going to use this new thing called a union symbol. A union symbol means or. So when you're talking about inequality signs that say or, we can also describe sets of values using or. And we use a union symbol. So union means or. And we use it when describing sets of numbers where we have more than one set. We're actually going to get into a different notation here that helps us describe more sets. It's called set builder notation. A little bit easier to use. But this is interval notation using a union symbol. So actually you might see it written a little better like this. So we got -infinity to -4, union in between our two sets with 3 and positive infinity completing it. So this would actually be a little bit better written as the answer to our problem here. Where does our function x squared minus 2x minus 3, where is it greater than 0? Well, in these domain sets. If I plug in any of these values from -infinity up to -4 and from anything greater than 3 up to positive infinity, I will get an output that is greater than 0. Kind of a long explanation, kind of a complicated problem there, but really all we're looking for are possible x values that give an output greater than 0. And so we just describe those possible values. Alright, let's see what happens if our parabola opens downward instead. Slightly different. Alright, so let's use this quadratic as an example. Now a is negative, so our parabola should open downward, and we're going to get a slightly different domain set here. So again, let's try factoring. In order to factor, we need our a value to be negative. So if we factor out a -1, then we end up getting x squared plus 6x now minus 1. Well, there can't be factors of -1 that add up to 6, so factoring is not going to be a good technique. So I always try second to complete the square. So if you don't know how to complete the square, check out that video first here. Let's try and complete the square. In order to complete the square again, a needs to be a positive 1. So again, we need to factor out that -1, but now we're only going to factor it out of the first two terms. I'm going to leave a blank here. And so that 1 is going to stay positive on the outside. And we're also going to leave a little blank to balance our equations once we bring something into our problem here. So to complete the square, we want half of this term squared. Half of 6 is 3. 3 squared is positive 9. So in order to balance our equation, because we just brought 9 into this problem from nowhere, essentially, we need to make sure that our equation is balanced. There's also this negative 1, so if we were to distribute negative 1 times 9, we would get negative 9. So negative 9 is how we balance our equation. Alright, now we can rewrite this as a binomial squared. We want the square root of the last term with our middle sign. So if we were to FOIL this all out again, we should get back up to here. I'll let you check that if you don't believe me. And if we get everything on the same side over here on the left side, we'll have our vertex or standard form. We'll be able to graph our parabola pretty easily. So we're going to add 9 to both sides. So if I add 9, and then I get a plus 10. So this is really this quadratic, just in a different form. It allows us to graph a little more easily. Our vertex is going to be h and k. H is going to be negative 3. K is going to be positive 10. So there's our vertex at negative 310. Negative 310 is way up here. And I know it's going to be opening downward, so we're okay so far. I can find more values, or I could solve for x using my quadratic formula. I'll let you do that if you would like. I'm going to cheat a little bit. I've already solved this problem just to save me some time on this video. But again, solve for x here using your quadratic formula. And you should get the values I'm about to plot on the x-axis, our x-intercepts. You should get close to negative 6.1 and close to negative 0.1. So real close to 0 here. And you can always check that using your line of symmetry. The vertex should always be right in the middle. It appears to be. So good so far. Now our parabola is going to do something like this. Kind of messy there. We're not really concerned about anything that happens where y is less than 0. Remember, we're only focused on where y is greater than 0. So really, we're looking for any x value that's in between right here. That's where our y values are all greater than 0. That's where our parabola lies. So what are the x values that give us this parabola? Well, they are from negative 6.1. I'll write it down here, negative 6.1. And it's an open. And it goes over to about 0.1, negative 0.1, excuse me. And that's it. There aren't two sets here. There's only one set. This is the only possible x values that give us an output greater than 0. So we only have one set. We do not need our union symbol. We only need that union symbol to describe more than one set. This domain is only one set, and these are the possible x values in interval notation that give us an output greater than 0. And the reason why this is important is because a lot of real-life situations are only concerned about outputs that are greater than 0. For example, if a fish is jumping out of the water, we're not concerned about the height of the fish when it was swimming under the water. For business purposes, we're never concerned about anything that doesn't give us a profit. We don't want values that give us a deficit. That wouldn't be very smart. So we're only worried about those outputs greater than 0. Other possibilities, I guess, would be projected things, arrows or cannonballs or people jumping. That isn't even possible in this range down here. We're never even going to see things that go under the ground or below really what we want our base to be right here. So a lot of times this is all you'll see. You're only concerned about outputs greater than 0. So there you go. Good luck using that inequality with quadratics.